Okay, let's get started. So if you have a quiz 9 and a homework 3 to turn in, make sure to do that. One thing to mention that if I don't remember, I'll say it right now. For the next quiz that you're getting today, it's not due on Friday. It's due the following lecture, which is Monday. So you don't have to hand this in Friday. And don't do the first question because I realized too late that the question was way too hard. And in fact, it's so hard I don't even know the answer myself. So, you can just do it yourself. Question 1, if you want to, you can try. If you have an idea of how to solve it, that'd be really good. But yeah, you don't have to do question 1 on there. Okay. Any questions since last time? Yeah.
Can we just talk about the exam a little bit, like other than get practice?
Yeah. So today, so what's on Friday? Exam. Woo! Anyone else as excited as I am? Woo! Yeah. So on the schedule, I have review for today. So the only things that will be on the test, or actually have the possibility of being on there, are anything regular languages. So nothing we've done on context-free languages so far will be on there. So the only things that you'll be tested on are DFAs, NFAs, regexes, regular grammars, the pumping lemma, showing languages are not regular, closure operations. I think those are the big things. So the way I like doing these review sessions is I don't know what you guys don't know. I have an idea, but it's really about you. So if you have a certain problem you want to do or a certain topic you want to revisit or something you don't understand, we can do that. So floor is yours. Yeah.
I have a quick question on closure operations, regular languages, right?
Okay.
Closure operations just mean regular operations, right? It's just concatenation, union, and climbing star, right?
Yes. Yeah. So those are the three regular operations, which are union, concatenation, and star.
And what it means to be a regular operation is that
it has nothing to do with regular languages.
Right.
I know. I hate it too. I hate it more than you do. But yeah, so they're called regular operations, but they have nothing to do necessarily with regular languages. The reason that they're called regular is that these are the operations of combining multiple languages to get a bigger language. And there's a certain regularity to which the strings belong to a language if you apply operations to them like this. So that's the reason why it's called regular, nothing to do with regular languages necessarily. Because when we'll talk about context-free languages, they're also closed under these. So yeah, it's not tied to regular. Other questions? Yeah.
Can you remind us of the intersection and why is it not there?
Yeah, so those are operations that still are defined. They're just not under the umbrella of regular operations. So regular languages are still closed under them, so they're not under the umbrella of regular operations. Yeah.
And that's intersection. What was the other one?
Yeah. So the other operations that we talked about are intersection, and what was the last one? Yeah, complement. Good. So those are the 5 main operations that we talked about. There were some other ones that we did in the homeworks, but these are the main 5. Yeah.
Sort of like a general question, but what would you recommend as the best way to review this?
So the best way to review is all of the assignments that we've done, all the quizzes that you've done, because I post the solutions for everything. All of the labs with all the lab solutions that I have have hundreds of videos on my YouTube channel about with a bunch of playlists with the same material, which you can go to as well. They're all listed in the syllabus, so yeah, there's plenty of resources available. The thing that I would most recommend trying to do is look at the questions that you were asked on the homeworks and the labs and the quizzes and all that, and slightly modify the question. So, for example, if we take a regular grammar and we remove one of the 4 types of rules that it has, do you still get the regular languages? Or is it that we don't get the regular languages every time? Another one might be, what if we have a DFA? Instead of having one start state, I have a bunch of start states that I could be in any one of the states that I want to be in at the start. So instead of one start state, have a bunch of start states. Another one could be, suppose that I've enforced that the DFAs you make have exactly one final state. A DFA, not an NFA. Do you still get the regular languages? Those types of questions. So like a small modification.
Where do you find solutions for this?
Your brain.
All right.
I mean, we can talk about those. I mean, I'm not going to ask those on the test because I'm already telling you what those are. But we can do some of those if you want.
Practice would be good.
So, okay. So what types of questions do you want to do? Do you want to do pumping lemma type questions? Do you want to do some of the ones I just said, or what?
Can we do the specific pumping lemma questions where, like when we're choosing W, like the string, it's not the case, so we're just replacing the N with P.
Oh, okay.
Fine.
Yeah, like fine.
Yeah, you won't be asked something like that.
Oh.
Let me do a more reasonable example. So this is kind of a weird language, but so it's the language of some number of zeros, let's say A of them, and then ones, let's just say B of them. And I don't want the number of zeros and ones to be too close to each other. So what do I mean by that? I say, by close, I mean, is either the case that A is less than the square root of B, or B is less than the square root of A. So if I have, like, say, 100 ones at the end, I better have fewer than 10 zeros at the front. So it's basically saying that one of the 2 lengths, either the zeros or the ones, is vastly bigger than the other one. So what do you think? Do you think this language is regular? No. And one litmus test that you can do is there some kind of dependence between A and B here, the length of the 0 part and the 1 part? Yeah, there's a dependence. So that would be a good litmus test to show that it's not regular. And in fact, it isn't. Proof done. Ryan at the front said that this is not regular. It must not be regular.
It's not a proof, but it's true.
Okay. So how do we get a convincing argument to show that this is not regular? Oh, yeah, contradiction. Okay, so let's suppose L is regular. If I can write regular. Okay, cool. L is regular. Proof done.
Then we have to say that there exists a pumping
Yeah.
constant for it.
Yeah. So why do we say that?
So that we can show through the decomposition of W into X, Y, Z that there's some conflict?
No. What I'm asking is, why does there have to be this pumping constant to start with? Think back to the proof. We had the DFA on P states, and then we fed a string of length at least P, which had the repetition of the state. So the P in our mind is representing the number of states in a DFA for this language. And we know, and we suppose that one exists because we supposed L was regular. So that's just to keep in mind. Okay, so there's a pumping constant P. What do we do now?
Pick a string within the language.
In the length.
Such that the length of X and Y is, such that the length of W is greater or equal to P.
Oh, okay, cool. So let's pick a string in this language of length at least P. So let's choose W equal, now I'll let you pick. So we gotta pick the string with some number of zeros and ones such that this condition is true, yeah. So ABP and then 1B. So yeah, so we can try square root of P minus 1. Well, what if P is not a perfect square? P squared plus 1. So I know that that is an integer. Well, P squared is an integer. The problem is that square root of P might not be an integer, so you may have to take like the floor or pick the integer at least P that's a perfect square. But yeah, so P squared plus 1 avoids that issue because we have the symmetric condition here. If we only had 1, then we would have to work with the zeros at the front to make them longer so that the 1s is always an integer. But yeah. Okay, so we pick this string. Is that guaranteed that this string will work? So what do we need to do? Well, we chose this string, so what do we know? What do we do now?
We know that the cardinality of X and Y is less than or equal to P.
Well, what are X and Y?
We have to deconstruct W first.
We got to deconstruct W in one way or all possible ways? All possible ways. That seems quite a bit, right? All possible ways to decompose that guy. Or is there a shortcut that we can do?
That's where you see X, Y, and Z.
X, Y has length at most P. So what do we know about the X and the Y part? They're all zeros. Okay, cool. So every decomposition is of the form X is, say, alpha zeros, Y is beta zeros, just like we've done before, and Z is the rest. So P minus alpha minus beta zeros, and then P squared plus 1 ones. Yeah.
One really quick question.
Yeah.
I have. I'm just kind of confused as to how that covers every decomposition. Because couldn't you just switch around the variables and have it like, oh.
Yeah. So the alpha here is just some number at least 0. So for any choice of alpha and any choice of beta subject to these rules, and alpha plus beta is less than or equal to P.
Yeah.
So we're handling all decompositions, but in one case. So the case handles multiple decompositions at the same time.
But we get to choose the case, but it just has to handle every single possible.
Right, yeah.
Okay.
Yeah, and then sometimes you may have multiple cases.
Because I was just wondering about like if there was ever a point where we need, because for like every single solution we always have that P minus alpha minus beta.
Yeah, it's because the first run of characters is all zeros with and P of them. If we had some different number, then it'd be that number minus alpha minus beta. But it may be that you have like 0, 1, 0, 1, 0, 1 at the beginning. And so you'd have to have multiple cases of whether x starts with a 0, ends with a 1, or ends with a 0. Yeah, so there are multiple cases that could happen.
Okay.
But this is uniform, so it's easier. Okay, so we look at all decompositions, fine. So what do we do? What's there? Oh, okay, cool. So let's pick an I to be something. So I'm not going to pick the I value for you. So what one do you think will work?
Zero typically works to make it not.
Zero
but I'm
typically.
not educated about it.
0 typically works. Would 0 help us here?
Probably.
Why not? Think about what happens. So if we have p0s at the beginning, and we take an occurrence of y out of the string, the length of the zeros gets shorter. So that means we have fewer zeros, but the same number of ones. Okay? But do we leave the language now? Well, the number of zeros is still less than the square root of the number of ones. So 0 is not going to help us.
If you can get p cubed, so, right? Because then the square of p squared is still not, that will be greater than p squared plus 1 squared, but
I don't think you need to go that far. What about 2?
just to
Well, let's try it. Let's just see. It may not work, but let's try it anyway. So x, y squared z is 0 to the p plus beta 1 p squared plus 1. Okay. Well, let's see. Is this string in the language? Because if it is, that doesn't help us. So we got to show that it's not in the language. Well, here's a pro tip. Whenever you see for some language something or something else, you have to check both conditions. So you need to be able to show that both conditions are not true anymore. So what I want to do here is look at both of those conditions. So let's just say the left side we're going to devote to a less than the square root of b, and the other side we're going to devote to b less than the square root of a, because we have two things we need to check. If one of them is false, that does not mean that the other one is also false. So you got to check both. Okay, so let's check the left path that says that a less than the square root of b. So what does the a here represent?
The amount of zeros?
Yeah, the number of zeros. So the number of zeros we got is p plus beta. And we're asking if that is strictly less than the square root of p squared plus 1. Is that true? Because at minimum, what is p plus beta? P plus 1. Well, is p plus 1 less than that square root? No. So since p plus beta is at least p plus 1, and p plus 1 is at least as large as the square root of p squared plus 1, then p plus beta is at least as large as p squared plus 1. So that first condition doesn't work anymore. So it's not true that a is less than the square root of b. And then, so now what about the other side? So this is saying that p squared plus 1 is less than the square root of p plus beta. Is that true? Well, let's see. Well, it's kind of dubious to say, well, there's a p squared on the left side and basically a square root of p on the right side. So that seems to indicate that p squared is just way too big compared to square root of p. But we got that pesky beta in there. So beta could be huge, which would drive the right-hand side too big. But what do we know about beta? It's at most p. So since beta is at most p, this, oh, no, not that. And p squared plus 1 is at least as large as the square root of 2p, then p squared plus 1 is at least as large as p plus beta. So all we're doing is we're saying that make the right-hand side as big as it possibly can, and it's still the case that the left side's bigger. So therefore, actually these are strict inequalities, but yeah. So if we make the right-hand side as big as we possibly can, and the left side is still bigger than it, it can't be the case that the left side is smaller than the right side. And so therefore, we have violated that condition too. Any questions about either of those two? Also a pro tip. This question actually was on a test. Okay? So it's not like I just made this up or anything. This really did appear on a test that I've given. Okay? Just so you know. But any questions on this question? So what can we conclude at the end? Yeah, it's not regular. Okay? Cool, what other problems you want to do? Yeah.
Can we do that thing when the regular grammar and you remove one operation?
Okay. That's a sensible question. So let's see. So what are the 4 rule types with the regular grammar?
Empty.
Yeah, so variable goes to empty, variable goes to terminal, variable goes to variable, and then terminal variable. Cool. So let's see. So I'm going to label those 1, 2, 3, and 4 for what the rule types we have. So let's look at the case where we eliminate 1, so left with 2 through 4. So in other words, I'm forbidding you from having the first rule type, but you can have any of the other 3 that you want. So what do you think? Do we get the regular languages or do we miss some?
Well, we missed the one that goes just empty.
Yep. So that's all you would need to show. So in fact, we are missing the language which just has the empty string in it. So it really does change the set of languages that you have. It may or may not change it very much, but it does change it. Yeah.
So, would this, like, would it work for any of them? Like would you get a variable language if you took the second one or the third one? All of them you would get a variable.
The problem here is that could we simulate the missing rule with other rules? So here with the empty string, if we just have the language with just the empty string in it, then there's no way that I can have the start variable eventually make the empty string, because the only rule types I'm allowed either go to another variable or produce a terminal at the point. So I'm dead in the water at that point. So with the other ones though, so let's actually look at this, because it's actually good. So let's eliminate the second one, but we have 1, 3, and 4. So I forbid you from making a single terminal, and that's it. Yeah.
Oh, I was just gonna get the solution.
Okay. Yeah. So
Because
well,
I think it should be the same. It would just be, instead of having 2, you just have A to B, and in this case, B could just go to the empty string.
right. So it turns out to be exactly the same. So the way to think about this type of question is to simulate A goes to little a. So how do we simulate that rule with any of the other rules? So what would we do here?
I was gonna say maybe add B equals to
Yeah, so that's getting closer, but where's B here? Because I just have capital A goes to little a.
rule 4.
Okay, yeah, so the idea is, well, we gotta do something like this, and then B goes to empty. That's exactly right. The key here, though, is what is that variable B? Well, if it's an already existing variable, by adding B goes to empty, I might change the language. So what does B have to be?
Is that the A?
Oh,
No.
like a different variable.
It has to be a new variable. So where B is a new variable. Now we have no issues because this variable is not used anywhere else, and so the only place where it occurs is if you're applying this rule, which means that you're going to make the empty string in the first place. Make a single terminal, then the variable only makes the empty string, so we're actually all good. Cool. Any questions on that? Okay, so let's do this one. So eliminate 3. So I think this one might be the hardest one because I can't think of a solution right away. So we're left with 1, 2, and 4. Yeah. Yeah, go ahead.
So maybe this is wrong, but all that A to B is doing is going to be like a different, set of rules, right?
Right.
So couldn't you just take all the rules from B and make A's to that?
Yeah. So this question we're going to actually address next week. So the reason for that is when we're talking about context-free grammars, we're going to convert them into a form that's really simple. And one of the steps is eliminating these types of rules, which are called unit rules. But we're going to talk all about that next time. But as was pointed out, the idea is, so the answer is yes. Basically just copy the rules of B up to A, then remove A goes to B. There's actually a slight technical problem here, which we're not going to address here, but that's the idea. So instead of just immediately going to B, we're going to just shortcut it by taking the rules of B and copying and pasting them up to where A is. So instead of going through the A to B rule and then through one of B's rules, we're just going to copy them up directly. And that does work, but there's other things that you need to do to be sure. But yeah, that's the idea. Any questions about that? So eliminating the first rule changes the set of languages. Eliminating 2 does not change it. Eliminating 3 does not change it. Let's do 4. So eliminate 4, left with 1 through 3. So what do you think about this guy?
I think it does change it. I think it makes us use only single character strings in the grammar.
Exactly. So let's see. Well, I can make the empty string, that's good. I can make a single terminal, that's good. I can go to other variables, that's good. But if I can't do the fourth one, then all I can really do is just hop around to other variables without generating a character. And at some point, I have to apply one of the first 2 rules to get a string. So this really changes the set of languages. So what are the sets of languages I get here? Well, so the ones I get, so this does change the set of languages. Well, what can we get? Well, we can get just the empty string, or just a single character for where A is a terminal, or we can get the empty set. Because I could have no rule produce a character at all, or epsilon. So you would just be hopping around to other variables, not generating anything ever. So those are the only sets of languages that we can get. More interestingly, we don't even get the finite languages, because we can't get languages with 2 strings in them. Sorry. Oh, actually, no, this is not quite right. So I should be more precise here. So this is really all the strings W, such that W is a terminal and any subset of this. Because I could have a bunch of rules that make a single character, and say like if I have characters A, B, and C, I could generate A with one, B with another, C with another, but I can do any subset of that if I want to. I can't get strings of length 2, definitely. But these are the only languages I can get. Any questions about that? That's actually an interesting exercise. Okay, what other problems you want to do? We have like 15 minutes.
So you asked the question, so my string sake is L star always, and we define that language.
Yeah. Oh, great question. It won't be on the tests, but it's a great question. So, is L star always infinite? Because this is actually a really interesting question. Where L is a language, I don't care if it's regular. It doesn't matter in this case. It's just a set of strings. That's it. So, is it always infinite? Well, if I have any string of length 1 or 2 or whatever, will this be infinite? Yeah, so it is infinite. Is infinite if L contains a non-empty string. That's definitely true. Because you can just repeat that string as many times as you like. So what are the language or languages that remain? If I don't have a string that's not empty. The empty string? Well, I mean the set containing the empty string. The empty set, good. So let's look at the star for each one of these. So for the first one, where we have the set containing the empty string star, that means repeat a string inside this language as many times as you want. Well, what happens if we put empty strings next to each other over and over and over? Still the empty string. Well, what string is always in the star of any language? Empty string. So what is this equal to? Empty string. Good. And that's not infinite because there's only one string in it. Cool. Well, what about empty set star? So no strings in the language at all. I'll ask the same question again. What string is always in the star of any language? Empty string is always in there. So empty string is always in there. Is anything else in there? So it says, take something from the empty set. Anything in there? No. So, and put it into this language. Well, there's nothing in there, so we're not putting anything in. Take two things from the empty set and concatenate them together. What do we get? Nada. So what is the resulting language? It's the same thing. So in fact, we have a complete characterization of which languages star are infinite. If it has any non-empty string at all, then it is infinite. Otherwise, they're both finite. Cool. Any questions about that? Yeah.
So are all infinite languages non-regular?
Also a good question. So let's think about that. So are all infinite languages regular? Because we've done as an exercise, I forget where we showed all finite languages are regular. Yeah. I mean, so any non-regular language has to be infinite. But the question is, are all infinite languages not regular? Oh, I see what you mean. I wrote it wrong. Thank you. Non-regular. Thanks. Yeah. So is this true? Or is there an infinite regular language?
We did one where it's like any, you could just do like one star.
Yeah, one star. That's an infinite regular language. And we know it's a regular language because No. Well, I mean, we could make a DFA, but what is this thing? It's a regex. So if you can make a regex for it, it's regular. Cool. So 1 star, yeah. So sigma star, we've done several like the strings that start and end with the same character because we made a DFA for it. Yeah. So there are a lot of examples, but any non-regular language has to be infinite, because if it were finite, we've already showed that all finite languages are regular. So yeah, so the only place that a non-regular language can be is an infinite language. Okay. Let's do another problem. Anyone else have a problem to do? Yeah.
Can we talk about that question you posed earlier, like if there was a DFA with infinite many start choices?
Not infinitely many, but I can choose. Yeah. So this is what the way that I have called this in prior classes is a multi-start DFA. So the idea is, if this is our DFA, and let's just say that we have some set of states right here, then what I can have in this model is multiple states that you can start at. You can pick any one of those 3 that you want to go to. Any one. It's completely up to you. And this DFA accepts a string if there is a choice of one of those 3 start states, such that if you start there, it'll accept. So if like the best choice to pick was that state right there, you can pick that one and we'll say it accepts. So are multi-start DFAs more powerful than DFAs are? Because clearly they're at least as powerful, because you get more than 1 start state if you want to. Yeah.
I'm going to say yes, because wouldn't this just be an NFA, but we're just, if we had an NFA and we had like a start that epsilon to all the starts here, it's the same exact.
So your answer should have been no, but the reasoning is right.
Oh, okay. Sorry.
Because I said, are they more powerful?
Okay, no, they're
Yeah, it turns out they are equivalent. And the reasoning is exactly as was stated. So if we do the following, which is we make a new start state, we epsilon our way to the other start states, then by the definition of non-determinism, it'll make a choice as to which of those start states to go to. So we just made an NFA for the same language. Well, that means that we still have the regular languages. Cool. Any, yeah.
If you have like an unreachable state that's not connected to anything, but then like in the multi-start DFA, if you put like a start state on it, that's the only way you could reach it. So isn't that like more powerful?
No, so by more powerful, I mean, does there exist a DFA for the same language? It does. It's so the way you're thinking more powerful is the language will be bigger. So that's definitely, or at least as big as what it was before. That's definitely true. But the problem is there still could exist a completely different DFA for the exact same language. So it's not the case that just because the language gets bigger, that doesn't mean that this model can accept a non-regular language. So by more powerful, I mean, could it be that this machine accepts a non-regular language? No, because we just converted it to an NFA. So let me show you one that actually it does change it. So let's just say that we have a not regular, but double R regular grammar. I just made that up. Is a grammar with the 4 allowed types, 4 allowed rule types as before, but also allows A goes to variable terminal in that order. So the 4 rule types for regular grammars that we had before goes to empty, goes to a single character, goes to a variable, and then goes to terminal variable. I'm allowing you a 5th rule type, which is variable then terminal. So you can have both of them. And I said before several lectures ago that it would change the model, but we never showed why that is the case. So can I recognize a non-regular language with this? So what is our currently favorite non-regular language?
0 to the end.
0 to the, everyone groans, 0 to the end, 1 to the end. So 0 to the end, 1 to the end. So that's the target language you may want to try. Well, what was our context-free grammar? Not a regular grammar, but just a context-free grammar that we made for this. So I'll refresh your memory. So we did S goes to 0, S1, or empty. So that's the grammar that we made before. But this is not a regular grammar. So is there a way that we can modify this grammar so that it becomes a regular grammar?
Like we put 0, so S goes to 0S, and then S goes to S1.
So let's see. So that's so this is what you're saying. So S1 or empty. So I think, yeah, so let's see. So it would generate a 0 on the front and then a 1 on the back, yeah. Yep, so that actually works. So the suggestion was to do a grammar like this, where if you look at the rule before, what we're doing is we're generating a 0 and, actually no, this won't work. So here's why. So look at these 2 rule types. We see that there's no correlation between the number of 0s and 1s that we make. So it can do the 0 rule as many times as it likes, and it does the 1 rule as many times as it likes. Whereas the grammar before, the 0s and 1s have to march in lockstep. So you make a 0 and you make a 1 at the same time. Yeah.
So do we have to do something where we have like another variable where it's like if we do a 0, then we must also do a 1 later on?
Yeah.
Or at least right afterwards.
Right. So that's the right idea. So let's make a variable called t, and then the t is going to do this basically the same suggestion as before, which is to do S1. And then we got to make the empty string with the S variable. So I got to say that S is the start variable in this grammar. So let's see what happens. Well, if I generate a 0 here, that means I got to go to the t variable. But the only rule associated with the t variable is going to S and producing a 1 at the end. So every time I produce a 0, at some point later, I'm going to produce a 1. Whereas before, there was no correlation between the two necessarily. So here, when we produce a 0, we produce a 1 later, and we go back up to the S variable and do it again. So here we're actually simulating the 0S1 rule above with 2 rules. Cool. And we needed another variable because we needed to force the derivation down the path through the t variable. I think we're out of time unless there are last minute questions. Yeah.
For the sheet that we can bring to the exam.
Yeah.
is it from the back?
Yeah. Anything you want. Yeah. My rule for cheat sheets is don't disturb the person next to you. But you can have anything you want on it. Cool. I'll see you on Friday.